There's not an awful lot in this lesson. Okay. Right, we can write that down, please. Thermodynamics. I forget, you need to remind, we have an assessment support hour, don't we? What I'm thinking is, we have it this week, don't we? We're nearly finished the essay. There's not too much left to do. I think once we finish the essay, I'll turn the assessment support into physics tutorials, because I don't really feel like I have the time to change one of the classes into a tutorial, because there's 17 topics left and there's only 18 classes. So we'll change the assessment support into a tutorial. But for this week, do we have physics on a Wednesday? Do we have physics on Wednesday?
Yeah, 1 hour.
Okay. We're going to lose that 1 hour on a Wednesday. Okay, if you can write that down, please. Thermodynamics. You got that? Yes? Okay. Now, before we start, let's try and work out the meaning of this word. So, the first half, thermo. What does thermo mean as a prefix? Sort of a heat, yeah. And dynamics? Movement. So, thermodynamics? Yeah. The study of how heat moves or transfers. Okay. So you don't need to write this down because we worked out the meaning of the word, but to be more precise, thermodynamics is the part of physics that studies the movement of heat between different objects. So we all figured that out from the name. But you also study other things in thermodynamics. So in fact, you study the change in pressure and volume, not just heat and temperature. And in fact, you often use a lot of statistics. Do you know statistics? Yeah, averages. Thermodynamics is useful because it helps us understand the world of the very small, how it connects to the very large. Now think about this. I said we use statistics in thermodynamics, and you might be thinking, no, we haven't. But if you think about the proof we had for the ideal gas law, not for the ideal gas law, for the E equals 3/2 PV. Do you remember this? Part of that proof was we had to talk about the average kinetic energy. Because you remember in the proof there was a part where you had the total energy divided by the number. Anyways, it's not something we study much on the IFY, but if you were to study this next year, you'll see that there's actually a lot of statistics in thermodynamics, a lot of averages and calculations like this. Anyways, not much for you to write down here, so we'll just continue. So we've seen that the kinetic energy of an ideal gas is found by this formula, which I just mentioned a moment ago, 3/2 PV. But consider we also know that PV equals NKT. Yep. Which is the ideal gas law. So if we put these together, we can say that now that's a typo. That should say 2/3. So let me fix that actually. But I'll write it down here. So we've seen that PV equals 3/2. Oh no, that's not it. E. Stop. Okay, let's try again. E equals 3/2 PV. So that means 2. Yes. Hey, here for me or for them?
Neither, the fob.
Oh.
Just the fob.
Don't we feel special? You need it for
lovely to see you though.
Yes.
Sorry.
This is for downstairs.
Yeah,
okay.
we all left the room and nobody had a key.
Well, I did that last time as well.
Thanks.
2 over 3 E equals PV. But we said PV equals N or T. So therefore, 2 over 3E equals N or T. Or in other words, E equals 3 over 2 N or T. Or, another way to write this is that E is proportional to T. Because if you make the T twice as big, then the E becomes twice as big as well. So the E and the T are proportional then. Thanks.
Thank you. Nothing better on TV now?
No, there's nothing on TV nowadays now. Nothing on TV. E is proportional to T. And another thing that you notice is if T is 0, then E must be 0. And if E is 0, then T must be 0. So not only can you say they're proportional, but it's also worth really pointing out that E is 0, that implies T is 0 Kelvin, and this is 0 joules. But when T is 0, that also means that E is 0. And that's actually an important property of the temperature. If you really, really think about this, you could even go a little bit further. If I divide this by N, I get E over N equals 3 over 2 or T. But this is the total energy, or the total kinetic energy, divided by N.
Oh, energy?
Which is average energy. So this is the average kinetic energy per mole. Although it doesn't have to be a mole, it could be a molecule. So it just depends on if you use N or T, or what was the other one, NK, if we're using Boltzmann's constant. So this is the average energy per item, I'll say. That is proportional to the temperature. And also we have this, the energy is 0, the temperature is 0. That means when the temperature is 0, what is the average energy per item? 0. But if the energy is 0, then we know something about its motion. It's not moving, because that's the only way the kinetic energy can be 0. So in our mind, this means that T equals 0 Kelvin represents when all the items have stopped moving. And this is why it's a minimum temperature, because there's nothing before not moving. There's only not moving and then moving. And that is the point I was trying to get at in this slide. So the key result here is temperature is actually kinetic energy, but with just a different unit. No temperature means no kinetic energy and no movement. So what do you need to write down from this? I think this is the key thing here. Yeah?
It's not true that K equals to P,
It kind of is true. It's not quite 100% true, because there is a difference in the units, because energy you're measuring in joules and temperature you're measuring in Kelvin. So it's not quite true to say they're the same thing, but they're extremely close. If you double the energy, you double the temperature, and vice versa. So it's not the same, but there's a strong relationship between the two, that they're nearly the same. Huh?
Is there value here?
Is there what?
Value?
Yeah, because if you look at this formula here, the only difference between the average kinetic energy and the temperature is this constant here, which is 3 over 2 times the ideal gas law temperature. So if you, for example, knew the temperature, you could know the average kinetic energy. I'll just write AVG equals 3 over 2 ideal gas law T. Let's give this constant a new name. We'll call it what letter? We've already used K. Let's call it C. So you can say the average equals C times T. So if you knew the temperature, then if you multiply it by this constant, you can know the average energy per molecule. Or if you knew the average energy per molecule, you could divide it by that constant and get the temperature. So that's the point I was trying to make here in this here. Temperature is kinetic energy, but with a change in the units. You have to multiply it by this 3 over 2R. Now we won't be doing that. This isn't a formula for us to use. The point you are to get here is this. This is the point. That the temperature is proportional to the kinetic energy, and 0 temperature represents 0 kinetic energy. So these are the two results I need, A and B here. Yeah. Continue. Yep. Okay. Oh, sorry. Do you have this? Continue. Okay. So, internal energy U. Sounds fancy, but it's actually quite simple. The internal energy of a solid, liquid, or gas is just all the kinetics and the potentials added together. So, as a formula, it's simply it's also the total heat, blah blah blah. There's a lot here. I just really need you to note this. The internal energy U is just all the energies of each molecule added together, which is all the kinetic energies plus all the potential energies. Of course, this you can never calculate because you can't know all the kinetic energies and all the potential energies of every particle in the gas. It's impossible. So the definition is more of a concept than an actual calculation. Anybody get to build a snowman? Nobody built a snowman? You built a snowman? You built a snowman? Yes, of course. There's a picture. Roll it. 3 sections. 2 sticks for arms.
Yeah.
No, nothing for the face. Just 2 arms, that's all. You don't need to write all of this. Really, it's the formula that's important here. Are you okay? Are you hungry? Yeah. Was that your stomach a moment ago?
Yes.
It's okay. You know, you have a big appetite for somebody so small. It's quite surprising. Like, how tall are you?
pretty sharp.
Yeah. But you have a big appetite. It's good. It's all the maths and the physics makes you hungry.
We used to eat more during the holidays.
Yes. Are you back to normal food? Yeah. Okay, continue. So, just to clear up exactly what we mean by heat, you probably know this already. Heat is a type of energy, and it's not physical. You can't hold heat. Okay, it's a type of energy. Heat has no mass, and heat can move from one place to another place in different ways. In thermodynamics, heat means energy which is moved between two things when one is hotter than the other. Heat is not the same thing as temperature. Now this is where it gets complicated, okay? So please listen carefully to the English. Please listen carefully. So, to be clear, the temperature of an object measures the average speed of the moving particles. So when the temperature is big, it means all the particles, they're moving very fast. Okay? This means that a swimming pool at 20 Celsius has more heat energy than a cup of coffee at 80. Now I'll try and draw that to help explain. Here is a big swimming pool, and it is at 20 Celsius, and then here's a cup of coffee, and this is at 80. And we'll call this T1 and this one here T2. So of course T2 is bigger than T1. Okay? But all that is telling me is that these particles are moving faster than these particles. But if I calculate the total kinetic energy here and the total kinetic energy here, which will be bigger? The swimming pool. Not because the particles move faster, just because there are much more particles. So, weirdly, we can say the swimming pool has more heat, but the coffee cup is hotter. You see, this is where the English is messy. The coffee cup is hotter means the temperature is more, but the swimming pool has more heat energy. So this is where it can be quite confusing with the English here. Yeah?
That means the heat is proportional to the
total energy.
total and the
Yeah.
molecules.
Yeah, because in other words, the total kinetic energy is like the heat energy. Is the heat energy really? So this one has more just because there are more molecules. Yeah. Is that okay? That English? Yeah. So you don't need to write that down. It's just explaining the problem with the English. Hotter means greater temperature, not more heat. Just be careful with that. So heat, or in other words, thermal energy, which is the same thing as heat. It's something which can transfer from one material to another. You can measure it. And it's not a material. You can't touch it or hold it. You can just transfer it from one thing to another. Okay, so there's heat in this, and I can move this heat to here, but I can't hold the heat. It's a bit like electricity, like electrical energy. You can't hold it in your hand. But you can kind of hold potential energy. You can kind of hold potential energy, and you can kind of have kinetic energy, but you can't really hold heat energy unless you're some kind of X-man or something. Yeah, you can make it too. Yeah. So these are the properties of heat. It's a form of energy. You cannot think of it as a material. You can measure it and you can transfer it. So 4 properties. So this I need you to write. Now you don't have to write the whole box, okay? This one here is saying that you can transfer heat. This one here says you can measure heat. This one here says you cannot think of it as a material. And lastly, heat is a form of energy. So these are the 4 properties of heat. If you can write that down, please.
Heat is a particle?
No, that's what I'm saying in number 3. Heat is not a particle. It's like a property of the particle. It's like a kinetic energy, you know. You can't hold heat.
Yeah.
You can't say, I have 1 unit of heat in my hand. You can say, I have 1 kilogram. You can say, I can measure 1 meter. But you can't hold heat. Heat has to be in something. You know, heat can be in the wall, heat can be in me, heat can be in the table. But my point is, I can't separate the heat from the material. You know?
There's heat, but we can't touch.
We can't touch it. Heat has to be in a material with a mass. Yeah. It means basically you can't hold heat. It's not a material. It's in a material, but it's not a material. So this can have heat, but I can't take the heat out and hold it. It's part of this. Yeah. So really, the point 3 is really saying heat can only exist in a material substance. That's the point. You can't separate from a material substance.
And can you calculate the heat?
You can. No, you can. We can calculate the heat in certain materials. It's much easier to calculate heat loss or heat gain rather than total heat energy, although not impossible. Yeah? Continue? Continue, guys? Yeah? Okay. So, next. Heat supplied Q is the energy that you pump into a system. For example, a train engine works because it gets heat energy Q from burning the coal. This heat is converted into work. I'll give you another example, okay? When you cook dinner, the Q is the heat you put into your food. And the reason you're putting the heat into the food, well, what is the reason? To cook it, yeah, but why? Yeah, you're trying to cause a chemical reaction. In other words, you're using the heat. You're putting the heat into the food to do work. You want to change the structure of the meat from raw to cooked. So the Q is the heat energy that goes in, and the reason you put Q into anything is because you usually want to do work. So you think about the train, okay? The train burns coal. Why does the train burn coal? So it can move. Yeah. So the Q is the heat you supply. I call it pumped into the system, because it's like you push the Q into the food or the train or whatever. So heat supplied Q is the energy pumped into a system. Did you write that down? Now, think about another example. Do you all know what a hot air balloon is? You know a hot air balloon? No?
Hot air balloon.
Yeah, the big balloon that you can fly in the sky with. Yeah. Now, what is the Q here? Well, if you've seen them, they pull down on a little lever, and you see flames going into the balloon, and it heats the air up. Yeah? This is the Q. And what work is the balloon trying to do?
Up.
Yeah, so it's trying to get potential energy from the Q. Yeah. Next definition. Two physical systems are in thermal equilibrium if no heat flows between them when they're connected by a path permeable to heat. What the heck does that mean? Does anybody know? Yeah. Does anybody know what this means? So, we say, if you look at my hands, this is A, this is B. They are in thermal equilibrium if no heat flows between them when they're connected by a path that allows heat to flow. So the heat from my hand here does not go into this hand. Why not? Simply, both hands are at the same temperature. Now, if I pick this up, this and my hand, they're not in thermal equilibrium because I can feel the heat leaving my hand and entering the water. This is the feeling I get when it feels cold. Yeah? Is that someone know? Or the opposite, if you put your hand on something hot, it's not in thermal equilibrium because you feel the heat entering your hand. This is the feeling of hotness. Yeah? So basically thermal equilibrium means two things are at the same temperature, and when they're at the same temperature, no heat flows between them. Get the idea? Yeah.
This is thermal equilibrium.
Thermal equilibrium means, I could say this and this are at thermal equilibrium because if I put them together, no heat flows. I don't need to put them together. So for example, I know that I am probably in thermal equilibrium with him because if we put our hands together, I should not feel any heat flowing. Now of course this might not be true because he's sitting by the window, maybe his skin is colder, so I perhaps will feel heat flowing. You don't have a jumper on, so you're probably in thermal equilibrium with me. These guys look cold, so yeah, you look very cold, so I'm sure there will be a heat flow this way. Okay, did you write this definition down? Thermal equilibrium. Yep. Okay. Well, I'll just put up the basically. Basically, if two bodies are the same temperature, then no heat flows when they're in contact. We say they're in thermal equilibrium. So, thermal equilibrium, fancy way of saying same temperature. Yeah. Continue, Bruce? Yep. Here is a very simple engine. Let's look at the different letters, okay? So, Q is the heat pumped into the engine. So, there's a heat that comes off from the coal. This is Q, okay? Now, two things happen. Two things happen because of the Q. Number one, there's a change in the internal energy of the water. What happens to the energy of the water? It increases. The potential energy doesn't change, but what will change in the water? Kinetic energy. So we say there's a delta U increasing. But something else happens with the train. Well, it'll start to move. So there's some work being done. The train moves forward. Using the conservation of energy, we can get a formula between Q, delta U, and W. What is the relationship between the three of them? What do you think? Conservation of energy. So what equals what?
Q equals 10G U plus W.
What do we think? Do we agree with him? He's saying the Q equals delta U plus W. What do we think? True? False? Or don't know? Don't know? Don't care? You see, he's very confident. I just want to see if anyone disagrees with him. Nobody wants to disagree with him? You all want to agree with him? Good call, because he's right. The Q will equal this plus this. So, the energy that goes in, that's the Q, that will equal the energy that comes out. And the energy that comes out is the work done by the train and the fact that the train is warmer. So two things happen because of the Q. It makes the train warmer and it makes the train move. So conservation of energy says the energy at the beginning equals the energy at the end. So the Q equals the delta U plus the W. That's the reason I have this picture here, to help explain. You don't need to draw this. It's okay. It's okay. I'm just trying to help you understand the three letters here. The conservation of energy states Q equals delta U plus W. Okay, so I need you to write this down. Okie dokie. Continue? Yeah? That's a yes. Okay. In the last diagram, heat energy was put into the energy. What the heck was I supposed to say there? In the last diagram, heat energy was put in, I guess, and the result was an increase in internal energy and work done. However, it's possible to do work and see an increase in heat energy. Shown below is an example to convert work into heat. So I'll explain this very simple experiment done by James Prescott Joule. You should recognize his name. This is where we get the Joule from, after this person, James Joule. So here was his simple experiment. Let me explain. He has a weight here, maybe like 100 grams, and this weight is connected to a wheel, and this wheel is connected to like a pin, and there's a rope around the pin. So what happens is, when this falls, this will spin around. Yeah? Now, can you see this is in some water? And you see there's two paddles here. And these paddles turn in the water when this wheel turns. So what he would do is he would turn, wind this up, this moves up, and then he holds it there. And he looks at the temperature. Then he lets go. So then this falls down, this starts to spin, and what happens to the temperature? It'll increase, yeah. What's happening is the potential energy here, when it hits the ground, this gets converted into heat energy in the water. So what he was doing was converting work, potential energy, into heat. Okay, that sounds fine. Nothing too amazing there, perhaps. But just so you know, it's possible to go both directions. So you can change work into heat, or you could change heat into work. Because that was what was happening in the last picture. We changed heat into work. And in this picture, we changed work into heat. What does this tell us? Again, it just tells us heat is a form of energy. And energy can just change its form. So heat can become potential energy. Potential energy could become electrical energy. It just changes its form. Believe it or not, when he did this experiment in about, I don't know, maybe about 1850, 1860, nobody believed it was true. if you can imagine that. Nobody thought it was possible to change work into heat because people didn't understand that heat was just another type of energy. So he did this experiment here. There's also another place you can see this at the top of a waterfall. You know a waterfall? So if you look here, here's the water up here, and then it flows down here, and here's the water up here. And this water will be warmer than this water up here, because what happens is this here has the potential energy, and here it has no potential energy. But that energy didn't disappear. That energy was converted into heat. So actually, what he did was measure the temperature here and measure the temperature here, and he showed that all the potential energy was converted into heat. Yeah?
Why is it not converted into kinetic?
Well, the thing is, the speed here is the same as the speed here. So, it can't really convert into kinetic energy, because if this is the same size as this, and if this was going faster, then the water would start to disappear, because the water is coming out quicker than it's going in, if that makes sense, you know? Imagine you have people walking down a hall, okay, and the people at the end of the hall were moving faster than at the start of the hall. Then what would happen to the hall? The people would start to spread out. But you don't see the water separating because this is moving faster than this. I don't know what other way to say it. I suppose it's like if you have a pipe. If 1 litre goes in 1 minute, then 1 litre must come out in 1 minute. Because if more came out, then there'd be water missing. And worse, if less came out, then the water is stuck in the pipe and starts to build up. So there can't really be a change in the kinetic energy so much. Okay. Nah. Yeah, so we just have to finish this lesson on the laws of thermodynamics. So there's 3 laws in thermodynamics. The first one is called the zero law. And the zero law states, if 2 systems are in thermal equilibrium with a third, then they're in thermal equilibrium with each other. I'll explain what that means now in a moment. Yeah. Yeah, no, that's it. So if these are the same, then these are the same, then yeah.
Same thing, too?
Yeah.
One of them get a energy or heat?
No, because they're in equilibrium. There's no transfer of heat. What does this mean? Simply, it means if A is the same temperature as B, and B is the same temperature as C, then A is the same temperature as C. I mean, this seems so obvious, doesn't it? If I'm the same temperature as him, and he's the same temperature as Bruce, therefore, I'm the same temperature as Bruce as well. It's so basic, it's why we call it the zero law. Because it's hardly a law. No, it's hardly a law, yeah. A is the same temperature as B, B is the same temperature as C, therefore, A is the same temperature as C. As simple as that. Okay. So what's the first law? The first law, believe it or not, is a law you already know. The first law is a conservation of energy. but for thermodynamics. So it says that delta U equals Q minus W, or as we saw it earlier, Q equals delta U plus W. It's the same thing. Now, why is this law useful? Well, remember earlier I said it was difficult to calculate the U. Do you remember me saying that? But it's not difficult to calculate the delta U, because the delta U can actually be found from doing Q minus W. The heat in minus the work out is equal to the change in internal energy. So it's not really possible to know the U, but it is possible to know the delta U.
What's the unit of heat?
Joule, because of the form of energy. And finally, the third law, which is called the second law. The second law says that heat cannot flow from cold to hot unless you do some work. So in other words, heat flows from hot to cold naturally, unless you do some work to make it go the other way. A bit like, think about it like this: water flows from the top of a hill to the bottom of a hill. Now, will it always do this? No, because you could actually push it back up, but you would need to do work to push it up. Same thing with heat. Heat flows from hot to cold, and it can only go the other way if you do some work. I'll give you an example. In your home, you have a fridge. Yeah. The fridge is pushing the heat out because naturally the heat wants to go into the fridge. If you leave cold food on a table, the heat goes from the hot room into the cold food. This is what naturally happens. So you need a fridge to do work to push the heat the other way, keep it out of the cold food. Does that make sense?
But if we leave like a hot cup of coffee.
Yeah, if you leave a hot cup of coffee on the table, then the hot heat from the coffee leaves the hot coffee and enters the colder air around it. But if you have a hot room and ice cream, then the heat from the room will enter the ice cream, unless you put it in a fridge, and the fridge does work to push the heat back the other way. The same thing with air conditioner in a car. The air conditioner in the car pushes the heat out of the car. Yeah. But again, this is obvious. If you have something hot and you have something cold, the heat will move from the hot thing to the cold thing. I mean, everybody knows this. You put something hot beside something cold, the hot thing doesn't get hotter, the hot thing gets colder, and the cold thing gets hotter. Hot, cold, this will get colder, and then this will get hotter.
But the hot thing gets cold.
Yeah, because the heat leaves it. You know, like,
Also cold isn't cold.
yeah, it's not, like, if I said this was at 30, this is my coffee, and this is my ice cream. Let's say this is at, I don't know, -2 or something. The heat will flow this way. So after some time, maybe this is 25, and this is maybe -1. So this has gotten warmer, and this has gotten colder. You would be very, very shocked if after 10 minutes your coffee was at 40 Celsius and this was at -4 Celsius. I think if you really think about that, that would be a shocking result. That you put your coffee beside your ice cream and your coffee magically got hotter and your ice cream magically got colder. You know this doesn't happen. It's because of the second law. The heat moves from the hot to the cold, never the other way around. In fact, the other way around is ridiculous from our experience of day-to-day life. Yeah?
There's the coffee,
Yeah.
ice cream
Yeah?
in the room.
Yeah, well, beside each other on the table. Maybe here's my ice cream and I put right beside it my coffee. Yeah? Okay? Yeah. Okay. Question?
Why is it not U equals Q equals W?
U equals Q equals W. Yeah, we have delta U, Q equals delta U plus W. The reason is because it's kind of because the time, like this is time 1 and this is time 2. These two things happen at the same time after this has been given. It's a bit like if you have one snooker ball and it hits two snooker balls. We don't say the energy here equals the energy here plus the energy here. We say these two added together equals this one. It's because these two happen at the same time. I think I have a feeling I know what you're thinking. You're thinking the Q makes the U and then the U makes the W. Yeah. And then you would say Q equals U equals W. But that's not what's actually happening. What's actually happening is the Q makes the U change and the W at the same time. It's not a Q, a U, a W. It's a Q causes the U and W at the same time. You're not happy with this?
Why is it at the same time and like it causes U first, then only it causes it to move?
No, not necessarily. When you heat the engine and the train moves, the engine gets hot and the train moves at the same time. It's not like you heat the engine and then after a few minutes when the engine gets warm, the train starts to move. Like if you think about when you turn your car on, the car moves at the same time as the engine starts to warm up. So at the beginning, the engine is slowly warming up as the car is doing work. The two things happen at the same time. If what you say is true, then when I provide U and the train warms up, I have to wait until this is finished before this can happen. But these happen at the same time. I don't know if you don't seem too happy with that. Yeah. Let me go back to my picture. Okay. So here's the Q. When the Q goes in, two things happen. The U increases and it makes steam to push this. Now, okay, it is true at the very, very, very beginning, maybe you do have to wait a few seconds until this can move. But after a few seconds, once it starts moving, the Q here is doing two jobs. It makes the water hot and it also makes steam at the same time, which will make the work. There's no, we don't consider this event after this event. We consider these two happening at the same time because of this happening.
But I thought you need to cause the water to steam up before you...
Yeah, that's what I'm saying. Like, okay, technically, maybe for the first few seconds, you have to wait for the water to get hot enough to produce the steam. That's true, yeah. I suppose Q would equal delta U equals W at the very beginning. But that time can be actually very, very small. Once you have a very hot fire, water will really quickly turn into steam. Like if you imagine you have a really, really hot fire and you throw a little bit of water on it, instantly it will become steam. So just like with the car engine, it only, like when you turn the car engine on, how long until it starts moving? Maybe 2 seconds, 3 seconds. Okay, anyways, let's see what's the next slide thing. Yeah. Can I just see what questions I gave you now? Now, I was told by the person who is writing your physics exam that these questions are not something that will be on the exam. So, the only thing I know about your physics exam, because the only thing the person who's writing the exam told me, is that these are not on the syllabus on the exam. So, with that said, I only need you to do one of these questions, because one of them I think is quite interesting. We have this idea of a minimum temperature. What is the smallest temperature possible? Yeah, minus 273, isn't it? Or in other words, 0 Kelvin. But you might be wondering, well, if there's a minimum temperature, is there a maximum temperature? And that is what question 6 is about. So I just want you to take just a couple of minutes to try and do number 6. Number 6 is calculating a maximum temperature. Yes? For end of semester 1, that is me.
Oh,
That?
wait, but then
You just
you say